Hey guys, what's up? Eddie Aho here with KissAnalog.com. So today we are going to cover diodes or bridge rectifiers or rectifiers in general and power supply. We're doing this to support the power supply design we're doing for the audio amplifier, and I'm going to walk you through how diodes work in a power supply. And we're going to do a bridge rectifier, and I'm going to bring you into a circuit, and we're going to use a simulation package. I think it'll go kind of smooth this way. Let's do this thing. Okay, welcome to Understanding Bridge Rectifiers. We are designing a power supply in another video series, and I wanted to go into a little more detail about how rectifiers work. Diodes. Diodes used in power supplies we often refer to as rectifiers. They rectify the voltage, make an AC voltage into a DC voltage that we can use. What we have here is a circuit with an AC waveform here, 60 Hertz, and it's 100 volts in amplitude, plus 100, minus 100. This is a voltmeter showing the AC waveform, and we have a transformer in our power supply, and in this example it's a 10 turns to 5 turns, a 10 to 5 turns ratio. So if we had 10 volts on this side, we'd get 5 on this side. However, we do have 100 volts, as I said, 100 volts peak, so we'll get half of that on this side. We'll get 50 volts peak on this side. And then I have a 1 kilo ohm resistor here as an example load. This is our ground symbol. We have a ground symbol on both sides. The symbol's the same on both sides, so in this case we're tying our output ground to our input ground. It doesn't matter, it's just for simulation purposes, but when we're looking at signals it's in reference to ground. And so okay, let's look at the voltage on the secondary side of the circuit. By the way, this is a primary side, primary power, and this is secondary power. Secondary power is derived off of an isolation transformer, and that's shown by a coil here and a coil here with 2 bars in between, meaning that it has an iron core or some kind of core, ferrite core or iron core. So it's not an air inductor, and it's a transformer. So we're transforming and stepping the voltage down 10 to 5, which is 5 goes in 10 twice, so it's a 2 to 1 step down transformer. Okay, so let's look at the voltage here in this voltmeter. Well, this voltmeter, if you notice, sometimes this instrument does this, it switches my voltmeter upside down. So that's, see, and you can tell from the minus to plus signal, so it's tied in upside down. Let's just flip that around, start that again. Okay, so now they're both plus, so you see the waveforms are in the same phase. The green voltage being half the voltage as the blue one. The green voltage here, half the size of this blue voltage. And by the way, this is 60 Hertz we have here in the USA. So, okay, so pretty simple, right? Now, since we have an AC to AC waveform like we do in our power supply design, we do want to rectify and change that to DC voltage for our load. This load resistor right now is a 1 k ohm resistor. Let's just watch the current that's in our load resistor. Now, see the arrow? It's pointing up. That's electron flow. We're watching electrons flowing instead of conventional flow. And wow, it's interesting how this guy likes to flip things around on me. But you notice now that it flipped the meter upside down, so now it's plus to minus, and our current is going this way. So now our green and our orange waveforms are in phase with each other, and they're out of phase with the input voltage, only because the meters are hooked up backwards. So let's flip those around again. Okay, let's start that again. Okay, so now we're all the meters are plus up here to minus to ground. So everything's referenced to ground. And so it's all plus waveforms, plus voltage meter readings. So everything's in phase. Now the orange waveform kind of hides underneath the green waveform. Whoops. There they go. They rescaled. This thing auto scales. So over here we have 40 milliamps and minus 40 milliamps. So the orange current goes above the 40 milliamps. It's almost 50 milliamps. It's 49.9 milliamps. We had a little bit of voltage loss across the transformer. And so let's see the green waveform. We're 49.9 volts. 1K is 49.9 milliamps. Those are peak values. Okay, so that kind of shows what a transformer does as stepping down the voltage, and we can see what AC looks like on both sides. Okay, now let's introduce a diode into this circuit. A diode will only allow current flow in one direction. So instead of allowing this orange current to come below the zero line into the negative line, we'll only have the positive pulses. Let's see what that looks like. Okay, before we introduce the diode, let's introduce a capacitor so we can see what a capacitor does. We have this capacitor in here, and you see the plus minus, and they alternate as the voltage goes plus and minus across this capacitor. It's only 1 microfarad. Let's increase it. The green voltage is the secondary voltage, and the blue voltage is primary. It's 10 to 5, so we have 100 volts peak and 50 volts peak on the green. Okay, so let's increase the size of this capacitor to see what happens. Okay, there's 5 microfarads. I went from 1 to 5 microfarads. Don't see anything. Okay, keep on increasing it, and I'm up to 228 microfarads. Do you see any difference? Let's go to 5 millifarads. Okay, so the capacitor doesn't seem to do anything to the voltages, right? This capacitor has an impedance to the voltage, and it charges and discharges with the AC cycle. It allows a certain amount of current flow through it, depending on the value of this capacitor. But as far as helping us create DC voltage, it doesn't do that. We need that diode in here to help us do that. So that now we're going to go put the diode in and see what happens. Okay, so now we have the diode in the circuit. So this is our secondary side of the circuit. On the other side of the transformer, secondary, and that's primary. We know what our primary side looks like. So we're just, it's a 100 volt signal, 60 hertz. And we got 10 to 5 turns ratio. So we're going 10 to 5, that's 2 to 1. And so we're going to get 50 volts on this side. And that's what we've been looking at. Now we've added this diode, and we still have the capacitor over here. I've changed it to 1 microfarad, it's pretty small, and we have the 1 kilo ohm resistor. So let's take a look. Here's our AC waveform coming in through our transformer. First wave wasn't quite as tall, as I had to build up a little magnetic field in the transformer to transfer the voltage. So now now each pulse looks like the next. Every cycle is the same as before. Okay, so incidentally, because of the transformer I have in here, we're at 45.4 volts on the top and minus 45.4 volts on the bottom. So we've dropped a little bit of voltage in the, well, the diode's going to drop some voltage from this side to this side, so that's one thing. But we're still looking at this side. We haven't gone to this side of the diode. So we're going to see some voltage drop across the diode, but right here we're still on this side of the transformer where before we had 49.9. Well, with the capacitor and the resistive load, we're changing our load scheme a little bit. So now we've got a little bit of voltage drop through the transformer and we're getting 45.4 volts. Okay, that's just a simulation model of this transformer is all that is. Alright, so now let's look at the voltage on the other side of the diode. Okay, you see it started off flat here, and then as soon as the blue waveform went up, it went up, and see how it kind of it doesn't quite follow the blue waveform to the zero, kind of slopes off. That's this capacitor. Has a little bit of a charge on it, but not very much, right? That's not really helping us much, but you can see that there's a capacitor there. Now, the green and the blue waveform would appear to be right on top of each other. Okay, the green waveform's going to 44.5 volts. On this side we have 45.4. Okay, on this side we have 44.5. So we've dropped a little voltage across this diode. Okay, again we have 45.4 as a voltage on the peak, and 44.5. That's about 0.9 volts. It's hard to see on this scale, but you can just kind of see a little blue up on top, and you can see a little bit of a curve here. So let's make this capacitor a little bit bigger, because it's not what we want to do. Is we want to have very little ripple, and right now we have a lot of ripple. But what we have now is a pulsating DC waveform. It's no longer AC. This side's AC, it goes from plus to minus. This side now is only DC voltage, but it's pulsating DC. Okay? So let's see if we can make this capacitor bigger. Okay, grab hold of this guy. Okay, we're up to 5 microfarads. So at 5 microfarads, you can see that now it's got a longer charge, but still, it's almost down to 0 before the next waveform comes up again. Every time we get a charge waveform, it charges the cap back up. But then it discharges pretty quickly. So 5 microfarads isn't very big. I mean, we only have a 1K ohm resistor pulling a load off of that, but that was, approximately 49, well, it's about 44.5 milliamps. So it's not very much. Let's make that capacitor larger. Okay, there's 10 microfarads. So 10 microfarads, you can see that it charges and then it drops down, charges, comes down. Now, what I want to show you is an important parameter, is the peak current going through this diode. Before we're making this capacitor large, the current followed the voltage waveform. But now with this diode, we're only charging between this spot and that spot. Where the green touches the blue is where we charge. And when the blue drops below the green, we don't charge. Okay, so whenever we have that diode drop, approximately 0.9 volts, is where, in our picture here, it would be where the green seems to cover the blue. However, the blue is slightly above the green. So whenever the blue is above the green, current's conducting. Let's see what that looks like. There you go. Okay, the waveform's changing because this meter's auto scaling the waveform so we can see everything. But notice that as soon as the blue goes above the green, we get an orange pulse. And then the orange pulse turns off when the green drops below the blue, or I'm sorry, when the blue drops below the green. So the capacitor stays charged up and drops off. Okay. Now let's make this capacitor. I'm gonna drop the value of this capacitor again just to show you how that changes. Let's go back down to 1 microfarad. That's 1 microfarad. That's where we could barely see the green waveform having any charge at all. Just a little bit of a curvature right there. So now you can see the orange waveform looks much more almost sinusoidal. As soon as the blue crosses the green, you get kind of an inrush current, which we call it, because the capacitor is drained, so it charges quickly, and then once it does, then it kind of follows the green waveform. But once the green or the blue drops below, or purple, whatever that is, drops below the green, then the orange turns off again. So what's important about this is right now the the orange waveform is on for kind of a long period of time, which is good because the value right now is going up to about 50 milliamps. Okay, it's actually 47.6 milliamps. All right, so now let's make that capacitor big again, and what you're going to see is that orange waveform, since it only has so much time to charge that capacitor, it's going to put a lot, it's got to put the same amount of current into it in a shorter amount of time, so it gets very tall. Okay, spread it out. Okay, that's what it looks like. Okay, now let's go ahead and make that thing bigger again. I'm just go back to 10, and then we'll go larger than that even. But just so I can tell you what the value is, we're around 49 milliamps before. Now we're getting peak currents at 225 milliamps. You see that? And it's very peaky. When it first inrushes, when that current first inrushes into this capacitor, and I can show you what that looks like. We'll look at the current into this capacitor. Well, that's the current as it's discharging to the capacitor into the load. And you see how it has a sharp angle. So the orange has to also, has to help provide load for the resistor and charge the capacitor. So you can see the capacitor drops in voltage, and as the orange current goes up, then this red waveform goes up as it charges the cap. And then the cap kind of overshoots a little bit, and then it discharges down to the orange. So then it drops off, and it has to recharge again. So let's turn that off. It's kind of getting busy. Well, let's leave it on just for a moment. I'm going to make this capacitor even larger. Let's go to 50 microfarads. Okay. So now the cap's pretty big. What's happening though is our green waveform, our voltage out here, is starting to look better. Much less ripple. See, that's much less ripple. It's going up as a peak at 44.5 volts, and it's dropping down to 33.5 volts. So it's about 11 volts peak to peak. So that's still quite a bit. But you can see the current, and here, let me turn off one of these guys. You can see the current going through this diode is getting very peaky, and it doesn't look sinusoidal anymore. Now it just pops up, and then it almost drops right off. So it doesn't have that sinusoidal waveform. It's starting to become very sharp. When current and voltages become sharp, it's more noisy. So it's actually creating more noise on this primary circuit trying to provide power to this diode. Over here we're getting smoother to our power supply, which is what we want, but at the same time we're actually causing a little bit of a noisy issue over here. Okay, that's going up to, that current right now is going up as high as 602 milliamps. So we started off around 50 milliamps, we're all the way up to 600. We've gone 10 times the current peak from 1 microfarad to 50 microfarads. Okay, let's make this guy even bigger. Okay, there's 100 microfarads. Okay, at 100 microfarads, our green waveform's getting flatter. Now it's going from 44.5 volts to about 38.3 volts. So it's about 6 volts peak to peak, just a little bit less than 6 volts peak to peak. But our current, again, it looks like a shark's tooth. It's just very sharp, because it can only turn on during that part, you know, where the green waveform is not quite flat, where it has to get charged back up. It's only charging during the part where the purple waveform is above the green waveform. The voltage here has to be higher than this side so that it can flow through that diode. So it's 800 milliamps. Okay, let's make that 1 millifarad. We'll make it really big. Okay, there's 1,000 microfarads, 1 millifarad. Now you notice that first pulse, it had to charge up that cap, so it dropped the voltage. It made the voltage sag, so it actually had a big charge cycle. There's a big one there too, in case you missed them. Look at those big charge cycles making that cap big. Now we're charging that cap, they're getting smaller and smaller. So we're getting to more of a steady state cycle here. Alright, so this current going through this diode is up to almost 1 amp, 947 milliamps. So that's quite a bit. That has increased quite a bit. It's a very sharp peak, but look at the green waveform, nice and flat. So the voltage over here, right now, it is going from 43.8 volts down to 43.1, so it's only 0.7 volts peak to peak. Now, if you've noticed, the voltage has been dropping though. The DC value has been dropping. The peak of the green waveform has been dropping because we're getting more losses to the transformer and the diode as we increase those peak currents. Because we're all the way up to 1 amp now. Okay, so how do we improve on this? Well, see these purple waveforms down here, the bottom ones? We're only halfway rectified right now. We're only taking one of the pulses from the AC and sending it to the load. This other negative pulse, nothing's happening. We're only taking current on the positive side of the pulses. That's one cycle. One cycle is about 16.7 milliseconds. But at every half cycle, we're getting a negative pulse. It'd be great to get a diode to direct that negative pulse up to here. So when you think about it, this transformer, during one moment, let's spread this out a little bit. So it's going very slow. If you see these waveforms here, at one moment we got a positive waveform here, and then it slowly turns where the positives down here and negatives up here. So when that happens, if we could take these, if we could set some diodes up to steer that voltage and put that bump up here, so we can do that. We can use some more diodes, and we'll steer each waveform to the top side. Let's do that. Now, by the way, to do that, since I only have a single winding on this output, I'm going to have to use 3 more diodes to steer that. Imagine if I had one diode here going the same direction. Like this
current is going this way through the load and back this way through the transformer winding. It's going around this way. Okay, it doesn't flow through that ground and go anywhere that way. It just cycles through here because we're isolated from this side. So the current just cycles this way. That ground waveform, even though we're touching here, there's no current flow to that side. It's just all through here. So imagine if we had another diode facing that direction. Well, it really wouldn't do anything to us right now. We already are steering the current this way, but when we want to take the transformer winding and get both pulses, we're going to have to put a diode here, and that forces that helps force the current this way during one cycle, and then we'll use 2 more diodes to switch the waveform around so that we get that what looks like a negative pulse into a positive pulse on the top. Okay, so let's do that. Okay, so this is what we call full bridge rectifier. There's 4 diodes in a bridge. So now we have a diode. We have 2 diodes facing this direction. They're tied together. So whenever we get a plus waveform on this side relative to this side, it's going to go this way. Whenever we have a plus on this side, it's like we did before, it's going to go this way. Now let's follow that loop. Let me bring my pointer over here. We're going to go through this diode, through the load, back around here, and we're going this way, so we follow this guy to this side and then come back through the transformer. So we got to go through the transformer because that's our voltage source. So that's the loop right there. Okay, we're going to turn this on so you can see it. I just want to give you a heads up what to look for. Well, then that's going to happen during one side of the cycle, right? When the cycle flips around where this becomes plus and this becomes minus, then the voltage goes this way, or the current, I'm sorry, goes this way. Comes up here through our load. So it's always going through our load the same direction because we want DC up here. It's always going to be plus up here. Comes down, comes around, and then comes to this diode and through our transformer. So that's got kind of a strange path. Again, it comes through this diode, through here, down our resistor, around here, and it's got to find its way back up here, so it's this diode here. Comes to this diode and comes back there. So that's our circle. So these diodes are just steering diodes. They just help when the waveform is rotating back and forth, they steer the waveform properly, so we always have plus up here and minus down here. Okay, let's watch that. You can see the waveform, the green one here, and the blue waveform started right here. We get a plus bump. That bump there became plus now. See the bump here? These negative bumps are starting to become positive now. So we get a charge pump on the positive cycle like we did before, positive side, but on the negative side we're also getting charge cycles. So now instead of every 16 milliseconds, 16.7 milliseconds, we get a pulse. That's one cycle, that's 1 over 60 hertz. Now we get double that, so it's like 120 hertz. So we essentially we changed our waveform from 60 hertz to 120 hertz. Doubled the waveform, so we get double the charging pulses. And you notice on each trailing edge, it's a little bit of a bump like we got before with that 1 microfarad cap. Well, now you can imagine we don't need to have this capacitor as big because now the time between pulses is half. So let's start to make the capacitor larger. And by the way, let's watch the charge current. We're going to just look through one of the diodes because every diode is going to look the same, you know. So we'll just look through this diode, okay? Okay. Now, with only a 1 microfarad cap, we only get a sharp edge for just a moment, and then it starts becoming a kind of sinusoidal, kind of smooth, because cap's not very big. It doesn't take very much to charge it. Then after that, it almost follows the voltage waveform. there's a little bit of lag because of the capacitor, but let's make that cap larger and see what happens. Okay, we're going to go up to 10 microfarads from 1 to 10. Just jump right on up there. Okay. So 10 microfarads, we're at 200 milliamps. Well, it's 187 milliamps to be more precise. So we're getting a charge cycle here, obviously, because you can see the voltage gets bumped up. It's from the other diode. We can look at that too. So now the red one turns on, then the orange. So every cycle we get a pulse, and it's 187. Well, we had to kind of charge up the capacitor, and so now they're all charged up. It's about 177 milliamps. Now, just for reference, I didn't tell you what the current was when it was 1 microfarad, so we're going to just jump back down to 1 microfarads real fast, just to compare it to the half wave rectified signal. This is a full wave rectified signal. We're rectifying both sides of the waveform, so it's full bridge, full wave rectifier. Okay, so you see how the first few cycles has to kind of charge up the cap, and once it kind of becomes more of a steady state, then each waveform looks like the next. So the peak currents in these is about 46.8 milliamps. Now that was about the same as it was with the half wave rectifier, right? Even though we're getting double the charge cycles. Why is that? That's because our capacitor is being discharged every cycle, so it has to start over. So every one's the same. It's not until we start keeping that capacitor above ground, where we don't have to start from zero, where it really starts to make a difference on the charge current. So let's make that cap big again. Okay, so the first pulses, this is kind of causing some noise, but the first pulses were kind of big to charge up this cap, and then they settle down. They settle much quicker because we're getting double the pulses in the same amount of time. But you can still see there's some uneven, they're not quite even yet with, every pulse to the next, so it's going to take a few cycles to start to level out. Now, incidentally, our voltmeter over here, look how flat that is at 100 microfarads. Remember, we had to go, quite a bit bigger than that before to get it that flat. But now that we have double the charge cycles, we have 43.6 volts max and 40.6 volts min. So we have about 3 volts peak to peak with 100 microfarads. So that's pretty good. Now you may notice that the voltage is dropping again because now we have to go through 2 diodes with each charge cycle. So that's somewhat of a trade-off. Okay, we're going to make this capacitor larger. We're going to go back to millifarad again. Okay, there's 1000 microfarads, which is 1 millifarad. And you can see those first cycles really have to charge that big cap, and then the pulses get smaller. Now, this instrument changes the range, so it makes them look like they're getting bigger, but really it's just changing the range here, the scale on the side. So right now, through one of these diodes, we're getting about a half an amp. So anyway, you can kind of see what's happening. We're getting double the charge cycles. You can see that the blue waveform now is very flat. these peak charges before were almost an amp. Now they're around half an amp because we have two diodes. I mean, we have, you know, double the charge pump. So we're getting about 480 milliamps. So I hope that helps understand how rectifiers work and how the diodes are used for steering the voltage, and how the voltage drop on the diodes, even though we're getting a flatter voltage, we're getting double the pulses, we get 2 diode drops in a full bridge rectifier. And you can also see that with the higher currents we were getting some voltage drop across our transformer. So when we select these parts, we have to be cognizant of all those things. And I have a different current rating on each diode, so one diode's dropping a little bit more voltage than the other one. So you can see how the diodes, the capacitor, the transformer, all these things play a role in what you end up with voltage here. The other thing you can see is that by making the capacitor very large over here, we're getting really high peak currents over here. Okay, so what I've done here is I've turned on the current so we can see the current coming out of the power source, and that's a blue waveform. So you can see the orange and red waveforms, the pulse, charge pulses charging up this 100 microfarad capacitor, and we can see the blue is the input. So every time one of these diodes turns on, it pulls current from the input. But the input is AC, so you get pulse up here, pulse down here, pulse up here, pulse down here. This bridge rectifier, these diodes steer the current so they're all positive. So on this side of the diodes, we're getting just all positive pulses. But you can see by these large capacitors creating these high peak pulse currents that it's done so on the input as well. And that can be an EMI problem. So it would be beneficial for us to add a little filtering to help smooth that out a little bit. Now, let's turn off the current in the diodes for a moment. Whoops. There we go. Okay, so now we're just looking at the input voltage and the input current. And if you ever studied power factor in school, you would know that the power factor, you know, without the rectifier diodes, you'll see the current is AC waveform just like the voltage. And depending on if they're in phase, happening at the same time, or if they're offset, you get a power factor, a phase angle. When you add rectifiers, you get these pulses. It completely changes the power factor analysis. So now you have current happening in these large pulses. So that causes distortion, and it causes a phase change between voltage and current. And those two factors are what create the power factor with the bridge rectifier circuit. That's another whole topic. Let me shrink this down just a touch so you can see the arrow. So anyway, that's another whole topic, but for now, what we want to show is how the capacitor affects these peak pulses, and we did that so that we could get this voltage here. Let's turn that back on. We did that all so that we could get a nice smooth output voltage with very little ripple. But there's ramifications to that. Peak pulse currents. So we got to do things to make sure that that doesn't cause us noise problems. But our voltage now, and on this side of the circuit, we're going to have a nice clean power supply over here. It's just that we want to come back here and maybe do some filtering. But that's kind of an introduction to rectifier diodes in a power supply circuit. Hope that helps with understanding that and selecting these diodes for these high currents, because you're just charging during a small part of the waveform. So the average current is much lower than these peak pulses. So when we select these diodes and we look for these high current things, then you can see why. The other thing is we notice there's voltage drop across the diodes, so that's something for us to consider when we select our transformer. If we want a certain voltage over here, we got to take 2 diode drops into account. The transformer, it has to handle these high peak currents, so it's not putting out RMS sinusoidal current, it's putting out these big pulse currents. So if the transformer is designed for a lower steady state current, then there's going to be some losses in the transformer when it goes to these high peaks. These are all considerations. I hope you can see how the capacitor and all these things affect each other. Going to a full bridge is definitely worthwhile, even though we get an extra diode drop. We get 1 diode drop, but we get a much smoother output. We get charge pulses every half cycle, every 8.3 milliseconds. Alright, well, thanks for watching.